Okay, we're going to pick it up here where we left off. Seems like a good slot. So we've been talking about organic chemistry here. Um, last time, we talked about some stuff. We talked about some isomers, I think. And again, isomers, as we talked about, are things that have the same molecular formula, but different connectivity. And they will have some different properties because of that different connectivity. We talked about sort of drawing isomers and also how to know if you really did sort of draw an isomer versus just drew the same thing. Remember that if you pretty much kind of follow the naming and you name your two structures or however many structures you drew, and you do end up with different names, then you most likely drew isomers of each other. If you drew two structures where they do look different, but if you were going to name them, you would end up with the same name, then it's pretty much the same compound, just drawn differently. And those are with alkanes, means that we're looking at when we go to name alkanes, it's always pretty much everything is the longest carbon chain. We find our groups that are attached. And then again, we number the longest carbon chain, whichever way gives the groups the smallest number. And that again is for our alkanes, which are our single bonded guys. It is the groups that take the priority in terms of which way that you number. We got into a couple other organic groups, which were alkenes, which have a carbon-carbon double bond as its functional group, and alkynes, which have a carbon-carbon triple bond as its functional group. And these guys, again, are based off of really those 10 alkane names. But we do a couple of different things when we're dealing with naming these guys, as we talked about last time. First off, they will end in ene if it's a double bond, or they will end in yne if it is a triple bond. The sort of first part of the name is still based off of the first 10. So if we had a something like this, this would be 1, 2, 3, and 4 carbons there, which is based off of butane. Because it has a double bond, will become butene. And the other thing that we tend to have to do when we name anything with a double bond or a triple bond is once you get to a situation where there could be more than one spot where the double bond or the triple bond is located, you do need to give the location of the double bond or the triple bond. So in this case, we would want to give the priority in terms of numbering to the double bond or triple bond. So that is different than alkanes, where the priorities lies with the groups. When you have double bond or triple bond with alkenes or alkynes, it is the double bond or the triple bond that gets the priority in terms of which way you number. We always want to give it the smallest number. So in this case, this would be something like 1 butene. We need to do that to distinguish it from something like this, which would be like that. 1, 2, 3, 4, 2 butene. So right around 4 or so carbons is usually the situation where you do need to give the number. In this case, the number in front there is the number of which carbon the double bond, or you would do the same thing with triple bond as well, is located. Remember that is double bond, triple bond gets the priority, which means once you lock into place the numbering aspect of it, everything else that's there will also be numbered accordingly. So for example, here, if I had a get rid of a hydrogen here. For example, if I had me a chlorine right about there, that would put this chloral group at carbon 3, because again, the priority here would go with our double bond. So once we sort of lock in the numbering, any other groups that would be attached there would be numbered accordingly. That would then be obviously 3 chloral, 1 butene. We would still keep the number by the butene part there for the double bond location. Triple bond pretty much works the same way. You're going to kind of base it off the 10 alkanes, going to make the last part YNE. And once again, if there is kind of 4 or more carbons, you also need to get a location where the triple bond is located. That triple bond, once again, will take the priority in terms of numbering. Whichever way you need to go will give the triple bond the lowest numbering. And again, just like the double bond there, and once we lock it into place, in terms of that numbering, any other groups would be numbered accordingly. So if we had 3 bromol, 1 pentyne. If we were going to draw this, which we also talked about, we still do everything like normal. Always when we want to draw something, we want to work backwards. So pentyne would mean that I have 5 carbons, 1, 2, 3, 4, and 5. And 1 would mean that I have a triple bond at carbon number 1. And I know it's a triple bond because it ends in YNE, and it's at carbon number 1, which means I would turn that into a triple bond. And because I called that carbon 1, that means at carbon number 3 here, I would have a bromine. And as we talked about at this point, everything else is going to be hydrogens to get carbon to 4. So that would need 3, that would need 2, that would need 1, this would need none, and this guy at the end here would need 1. So when we draw these things, or when we name these things, double bonds, triple bonds takes priority, always lowest number, all the other groups sort of named accordingly. Any questions on that stuff there? Okay, so let's try a couple more here. And why don't you also draw, let's do, let's do 2 ethyl, 4 hexene. And let's also draw 3 chloral, 1 heptene. All right, so draw the guys on the right, name the ones on the left. See what you come up with. Here and see how we're doing. We'll start with the ones on the left here. Thank you. We got longest carbon chain. Remember that when we're doing that, 1, 2, 3, 4, and 5, it does need to contain obviously the double bond or triple bond. If there is a double bond or triple bond, so you can't go away from it, you got to have it in there. You could also, I think, get the same result there, 1, 2, 3, 4, and then go down to 5. Once again, it doesn't really matter which way you choose it, but might as well take the straightest way. Seems like a good one. Looks like 5 there is going to be our longest carbon chain. We then have basically this group hanging off of it right there. So 5 carbons in this case, going to be based off of pentane. But there is a double bond, which will then make it pentene. In this case, we want to give the double bond the smaller numbers. So again, you can probably see it, but going left to right would be the proper way here of numbering, as that would give our double bond a number of 2. Going in the other direction, you will end up with a 3 for the double bond. So since that takes priority, we do want to go in this direction. That means that we will add a 2 to that name. So that is 2 pentene for where the double bond is located. This is what I was talking about before. Since we've locked into place our numbering, our one and only group, which in this case is just a line, which should be a methyl group, right? Because there should be a carbon at the end of that. We'll then need a number of 4 in this case. So we'll end up with 4-methyl 2-pentene. Any questions on that name there? Okay, so looking to the one on the bottom there, we got some triple bond action happening there. We might as well just go straight across. That's going to be 1, 2, 3. Remember, that's 4, right? And then perhaps 5, and then 6, right? As we go through there. Again, with that triple bond, it becomes more linear. So there's carbons at the end of each of those triple bonds. So that is 6 in a row, which would be based off of hexane. Because there's a triple bond, it will now become hexene. Once again, here we want to number the triple bond to give it the smallest number. And in this case, you could probably see it. So we would want to go right to left in this case. And that would be 1, 2, 3, 4, 5, and 6. So that's going to be 2-hexyne, and there's nothing else attached there, obviously. So that would be the name. Any questions on either of those two names there? Obviously, going in the other direction, you're going to get a triple bond there at carbon number 4, which is larger than 2. All right, so we're going to draw some of this here after I switch around some numbers, which might be a little better. So we'll go backwards when we're drawing. So ENE means I have a triple bond. Hexane basically means I got 6 carbons. So 1, 2, 3, 4, 5, and 6. That double bond is going to be at carbon number 2. Once again, since you're drawing left to right or right to left, it really doesn't matter. I'm going to call this for me carbon number 1, which means my double bond will end up over here at carbon number 2. And because that's carbon number 2, for me, carbon number 4 would be over here. And that is where I should put my ethyl. And now everything else, again, is going to be hydrogen to get carbon the 4. Guy at the end has 1 line coming in, so needs 3 hydrogens. This guy has 2, needs 2. This one has 3 lines, just needs 1 more. This one also has 3 lines, needs 1 more. This guy has 3 lines, needs 1 more. And this one needs 3. This would be the condensed formula. Again, if we drew line, we would start with the 6 again. So 1, 2, 3, 4, 5, and 6. Here, I'm going to choose my carbon number 2 right there, as that's going to be carbon 1. It's going to put my double bond. So that'd be 2, 3, and 4. Again, would look something like that, would be your line structure-ish drawing. Any questions on that there? All right, so working our way backwards on the next one here. By the way, yeah, it was ENE. So I didn't do YNE, so I guess I did that right. So ENE would be a double bond again. This is going to be heptane, which is 7. I'll go this way. So here, 1 is where the double bond's located. So once again, I'm going to call this carbon number 1 over here. So that is my double bond in this case. Since that's carbon 1 for me, this would be carbon 3, which should have a chlorine. And now at this point, we will fill in our hydrogens. So 3, 2, 2, 2, 1, 1, and 2. And once again here, if we wanted to do a little line structure, 1, 2, 3, 4, 5, 6, 7, and carbon number 1 would be my double bond. 1, 2, 3 would be my chlorine in that case. Yeah, it looks something like that. If I get my head out of the way, it looks something like that, I suppose. Yes. Any questions on drawing, naming these guys? So very similar to how we do alkanes, again, just given the priority for numbering and everything to the double bond or the triple bond. All right, then let us talk about double bonds and sort of cyclic guys and how we go about naming those. So if we have a cycloalkene, which is basically a cycloalkane with a double bond, we do number it. And we do need to give the number of the location of where a group may be on the ring. So for example, if we have nothing on the ring, like this, just say like that. That is a 6-carbon ring, which is cyclohexane, has a double bond right there, which would then make this cyclohexene. Now, if we do have something on the ring, so we'll just do that, and we'll do this. Now, if we have something on the ring here, we do need to number where it's located, and you do have to go through the double bond when you number it. So let's take a, actually, I'll move it over one, just so we can kind of see a difference here. Actually, I'll put both. Put that there, and then we'll do this, for example. We'll put 2 here. All right, so in this case, this would still be cyclohexene, as there is obviously the same ring structure is the main thing. We actually have 2 methyl groups in this case, and we do need to number the methyl groups. So when we have a double bond in a ring structure, you do have to actually number through the actual double bond. And what I mean by that is you may be tempted to do, well, that's carbon 1, and then that's 2. We did not go through the double bond to get there, right? We kind of went away from the double bond. So your 2 options in numbering in this case is, because the double bond still takes the priority, even in a ring structure, you got to start numbering at the double bond, or in this case. So you could go this way, where you go, this is carbon 1, carbon 2, carbon 3, carbon 4, carbon 5, carbon 6, which means we would have groups at 1 and 6 coming through there. The other option would be to number in the opposite direction, which would be, this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4, this is carbon 5, and carbon 6. Once again, we're numbering through the double bond, not away from it. And that would put groups at 2 and 3 in this case. And in this case, the lower number will actually be the 1 and the 6 in this case, right? 1 is less than 2. So we would actually want a number in the opposite direction there, giving us that lower number for that first methyl group in this case. So we would actually want a number going this way around the double bond. And this would give us a name like 1,6-dimethyl cyclo, 1,6-dimethyl, because there's 2 of them, cyclohexene. You do not need to give the location where the double bond is in the ring structure, because it's always assumed to be carbon number 1, but you do need to use the double bond as your starting point for numbering anything else that may be on the ring. Question? Yeah. Well, 1 is less than 2, so you always want to go with the lower number. Yeah, so as odd as it sounds, because that first number is still lower, then that will give you the lower number. Yeah. Other questions? All right, and that's what we see here. So once again, in this case, as I move it, we look here, we have a 5-member ring, which means it's going to be cyclopentene, ENE. And numbering here, we could go as they did here, 1, and we're going through the double bond. The other option would have been to go 1, 2, 3, 4, and 5, which would give us our group at carbon number 5, which is obviously a larger number than going that way, which would be 3-methyl, as you can see here, cyclopentene. The one thing that you can't do is start at this carbon and go to here, 1 and 2, because you did not go through the double bond. So you have to number through the double bond. So you would not be allowed to do that because you did not go through the double bond to get to those groups. So that's why really those are your two options in this case, and the 3 being the smaller numbers, the way you would want to go. So that's one important thing to remember when you got a double bond in a ring structure. You got to number through the bond. You can't go away from it, even if it may give you a smaller number, just going directly to the groups. You got to include that as part of the numbering because, again, the double bond should take the priority. So it's got to have that numbering, smaller number, which means you got to go through it to give it the sort of the smaller number. Any questions on that there? All right, then why don't you name these guys, and why don't you also draw? Let's do okay, so let's take a look. Obviously this one here we just did, I guess it looked, but we got 1, 2, 3, 4, 5, and 6. So that's a 6-member ring, which again is based off of cyclohexane. We have our double bond happening there. So we got a little cyclohexene. Once again, here we don't need to give the number because there's no other group attached. And even if there was, you don't need to give a number because wherever that double bond is located, it's assumed to be carbon number 1. So that's all you need to call it. Any questions on that one there? Here we have a 5-member ring, 1, 2, 3, 4, and 5. That's based on cyclopentane. Because of the double bond, that will be cyclopentene. We do need to number our 2 groups here, and we have basically 2 methyl groups, which is going to make it a dimethyl situation. In terms of numbering, we have 2 options. Remember that you do need to go through the double bond, which means you could start here and go counterclockwise, 1, 2, 3, 4, and 5. Or you could start at this guy at carbon number 1 and go clockwise 2 and 3. And it looks like going sort of clockwise here is going to give our groups there the smaller number of 3. And in this case, that would mean that we have 3, 3. You do need to give the number twice, 1 for each of the methyl groups that are there. We're going to have a dimethyl, squeeze it in, cyclopentene. Any questions on that one? Obviously, if you went the other way, that's going to be a 5, which is a larger number. In this case, we're going to give the sort of priority numbering to the groups, as the double bond really doesn't get numbered because there's wherever it is going to be carbon number 1. Question? Yeah. What's that? You do. So you do need to give the number of each group, regardless if they're on the same carbon or not. So if they are on the same carbon, you got to give the number twice. That tells people that both of those guys are on carbon number 3. Other questions? Okay, we're going to draw here. So we'll still start backwards. So that is cyclobutene. So that's a square. That's 4 carbons. So I'm just going to draw a square-ish type thing. Sort of squarish. ENE means that there's a double bond. And since you're drawing it, you really could put the double bond wherever you like. I'm going to put it up here on top. So that takes care of that. Now that I did put it up on top, I have really one of 2 things I could do. I can number this 1, 2, going through the double bond to 3, and that is where I would put my bromine. By the way, if I started at this guy's carbon number 1, 2, I could also put my bromine on that side rather than the other side. It's the same guy just turned, basically. Yeah. Other questions on drawing these guys? So the key on this one, as I mentioned, make sure you do number through the double bond if you have a cycloalkene, and again, whichever way will then give the groups a smaller number as you go across. All right, so let's talk a little about some consequences of double bonds and alkenes, and it brings up another type of isomer that can develop, and that is because of a couple of things. First thing is this: in a single bond situation, These groups are not locked into place. You have basically free rotation around that single bond, which means you could spin it around as much as you like. Maybe if you built the model of a single bond, you could actually do that with the model. It will swing around as much as you like. There's free rotation about the single bond. But what happens when we lose those hydrogens and we drop in a double bond into that location, it really kind of locks everybody into place, which means you lose the ability to freely rotate around the double bond. Otherwise, it's going to break if you try to do that. So it won't be able to do that. And what that does is it creates two types of isomers, which are known as cis and trans isomers. Cis means basically the same side, and trans means basically the opposite side. And what we're talking about is the carbon-carbon double bond. So you could have a group on the same side, which would be cis. You could also have a group on the same side, which would be cis. But you could also have some groups here on opposite sides, which would be trans in this case. So when we look at cis and trans isomers, we always want to look at the double bond, and we want to really find four groups that are attached in that double bond, two on each carbon, and we really want to kind of see their location relative to each other when we look at it. Now, will we always get a cis and trans isomer developed? The answer is no. So there are certain situations where you will not get a cis or trans isomer that can develop. But how do you know you can get an isomer or cis and trans isomer? There's two things that pretty much you have to look for. So when you're looking at this carbon-carbon double bond, you need to make sure that on each carbon in the double bond, there are different groups attached. So you need different groups on the same carbon. And second to that is you need two groups that are the same on opposite carbons. So in this case, in my example, this B is on this carbon, this B are the same on opposite carbons. So those are the two things that you have to look at to determine whether or not something could do a cis or trans isomer. You have to look at each carbon in the double bond, and it's only the double bond that you should be concerned with. And are there two different groups on each of those carbons? Secondly, you need some type of group that's the same on opposite carbons. By the way, in this case, this would be a cis or trans isomer in my example. It would be a cis as each of those B's are on the same side of the double bond. So in this example here, this would be a cis isomer as those guys are there. Now, when we're dealing with cis and trans isomers, anything attached to the carbon in the carbon-carbon double bond is considered a group, including hydrogen. So you could kind of look at hydrogen as a group, even though normally we don't look at it as a group. But when we're looking at cis and trans, we would look at it. So when we look down here, we would want to focus in on this carbon-carbon double bond. And this carbon has a chlorine. This one has a hydrogen, which are different groups. This carbon on the right has a chlorine, and this one has a hydrogen, which are also different groups. So that means this can be a cis or trans isomer because they actually share, as it's highlighted here, chlorines on opposite carbons. So we have different groups on each of the carbons, same group on opposite carbons. In this case, it happens to both be above the double bond, which means they're on the same side of the double bond. And this would be cis isomer here on the left. We could look at our double bond here. And once again, chlorine and hydrogen, different groups. Hydrogen and chlorine, different groups. In this case, our chlorines are opposite of each other, and they're on opposite carbons, and that would make this guy a trans isomer in this case. So that's really important. You got to have different groups, same groups on opposite, and it's really those same groups that you want to determine sort of are they on the same side or opposite side. Now, for example, if I had something like, say, this here. Can this be a cis or trans isomer? I heard cis, trans, and some people shaking their head no. That's like 3 answers. We're getting that. So the answer is no, this cannot have cis or trans isomer. So let's see why it cannot. It cannot because we definitely have a double bond happening here. But now when we look at the double bond on each of the carbons, remember we do need to make sure we have different groups. So this guy and this guy are different. So that's good. But that's a hydrogen, that is the same on the same carbon. So because there's 2 hydrogens that are the same in this particular example, are 2 groups that are the same on the same carbon, you cannot have cis or trans in this case. So you got to make sure that both carbons in the double bond, different groups. The same group needs to be on opposite carbons, either on the same side or opposite sides of each other. Any questions on that there? There's a lot of fingers there doing these things, but yes, cis, same side, I think, in the thumbs on this one, and thumbs going up and down on that one there. That's a good choice there. So when we look at these guys, like I said, we can look at hydrogen. So if we look at this, we have carbon-carbon double bond. That's a methyl group. That's a hydrogen. That's a methyl group. That's a hydrogen. So once again here, different groups on the same carbons. Similar group on both of them is the methyl in each of these cases, and they're on the same side of the double bond. So that would be our cis. To butene, we do add cis to the front of the name and trans to the front of the name if necessary. And once again, if we look at our double bond, we have methyl group, hydrogen, hydrogen, methyl group. Methyl groups now are on opposite locations of the double bond. So that's going to be our trans in this case. Yeah. All right. So naming these guys, we do put cis or trans in front of it. And when we go to name these guys, it's really important to look at here. We got 1 carbon, 2 carbons. So that is ethene, ENE, because of the double bond. Because there's only 2 carbons, there's no need for a number because it could only be between the 2 carbons. In this case, we have a carbon 1 and 2 dibromo, and it is cis as they are on the same group, same side there. So that is cis 1,2 dibromoethene. What's not drawn here because this line structure is there are hydrogens, right, hanging down there as well. That would be there. In this case, this is our 1 carbon, 2 carbons, which is again our ethene. We have our 2 bromines, 1, 2 location, and these are opposite of each other, which is trans in this case. Yeah. Any questions on that there? All right, so for each of these, decide where they are cis and trans and give the proper name. Why don't you also make sure on the left-hand side here, these 2 groups are different, which they are. We want to make sure that these 2 groups here are different, which they are. Now, the group that's the same on opposite ones, there's actually 2 of them. You could look at the chlorines, right? You could also look at the methyls, that both will tell you the same. Either one that you look at, they're both on the same side, right? Which means we have a cis happening here, right? If we come down to the one below it, we isolate our double bond. This is different groups. This is different groups. Opposite carbons have the same group. You could look at the bromine. You could also look at the methyl group in that case. And in this case, they are both opposites of each other, which means that this guy is a trans in this case, as they're opposite. Question on those 2. Here, looking at the double bond, different groups, similar group on opposite carbons, and they're also opposite of each other, which means this guy should be trans. First off, any question on how to identify cis or trans here? At this point, we want to name it, so it's important to probably, get rid of all your scribble first and then try again. So let's do that. All right. Get back. All right, so still want to look for the longest carbon chain. So that's like a 1, 2, 3, and 4 situation happening here, not just the double bonded carbons, which people seem to focus in on when they have these guys. So that is 4 carbons in a row that has a double bond. So that is a butene in this case. We need to give the location of the double bond 1, 2, 3, or 4. In this case, it really doesn't matter which way you go numbering. The groups are going to end up on the same numbers, which in this case is going to be 2 and 3 for our dichloral. But before we do that, we do need to maybe lay up a 2 in there for our 2-butene, where the double bond's located. And that's going to give us 2, 3 dichloral 2-butene. And this was cis in this case. Any questions on that name? So sometimes people, when they look at cis and trans, all they focus in on is the 2 in the middle, and everything's ethane. No matter what happens, there's only 2 carbons. So remember, still want to look for those longest carbon chains. So if we do the next one, we're going to end up the same. 1, 2, 3, and 4 coming across this way. And again, that's going to give us our basically 1, 2, 3, and 4. So it's going to give us still our 2-butene. Our groups here will be at carbon 2 and 3 on this one as well. So that's going to be 2, 3 dichloral. I'll go above as I ran a room there. 2-butene. And this was trans, I believe. So this would be trans. 2, 3 dichloral 2-butene. Yes. Question? Yeah, that would work. Bromine is good. Thank you. Well, it's just want to make sure everybody's paying attention. All right, screwed up pretty badly there. That's probably more like it. All right, so thank you very much. So you're correct. It is 2, 3 dibromo 2-butene. Thank you. I think I had chlorine on my mind from looking the one above it. All right, so we're coming down here. We're going to end up with coming through this way. That is again our 4. This is going to be just trans 2-butene, as the hydrogens obviously are not going to be named in the naming part of it, although we do kind of consider them groups when we're looking for cis or trans in that case. Question on that one there. All right, now we're going to draw. So we're going to go backwards here, and we'll hope for the best. So we're going to go with 5 carbons. Now, when you're trying to draw something cis or trans, I personally think it's a good idea not to draw a cis or trans, but just to draw it like normal first, and then kind of draw your structure afterwards. So I'm just going to draw it like a normal guy here, which is 5 carbons. My double bond is going to be at carbon number 2, which is why it's 2-pentene. At carbon number 2, it will have a chlorine. At carbon number 3, it will have a chlorine. And now I could really just fill in my hydrogens at this point. So all I'm doing here is pretty much just drawing it like normal, not really worrying about cis or trans at this point. So we should hopefully be good there, I hope. Yeah. Now that I've drawn it like this, what I would want to do perhaps is look at my carbon-carbon double bond. And honestly, anything sort of attached to my carbon-carbon double bond here, we will look at and sort of put it there. So that is 1, 2, 3, 4. That is too many hydrogens there. There we go. Thank you. There we go. That's much better. less hydrogen. I know, hell, wasn't my greatest class, what are you gonna do? But if I could get through organic, it's everybody can. All right, now that looks a lot better, I think. So in this case, now that we have our carbon-carbon double bond, we could really circle our 4 groups that are attached there. Now that we got that extra pesky hydrogen out of the way. And now I could just go back and really draw it the way I need it. In this case, the groups that are the same on opposite carbons are the chlorines, right? And that means I would start with my carbon-carbon double bond. And since we're looking for trans, I could just draw my chlorine down, my other chlorine up, for example. And I could do my other groups going this way and just kind of build out my trans drawing at the end. So sometimes it's easier just to draw it like normal, isolate the double bond, and then start with the double bond and just kind of put your groups in the right orientation for what is needed for cis or trans. And don't have extra hydrogens, apparently. Has any questions on that there? All right, so that is cis and trans isomers. Let's talk about some reactions then that these double bond guys sort of go through. And when they do go through, they pretty much do what's referred to as an addition reaction. So when we looked at alkanes, they did a substitution reaction, which means one guy comes in, one guy goes out. In an addition reaction, pretty much everybody just comes in. And so, for example, we have a double bond happening, and we're going to add something to it. And what happens is, in this case, the way it is at this particular moment, if I wanted to put both of these guys on, one's going to go to one carbon, one's going to go to the other carbon, I could not do it exactly the way it's drawn because I will have too many bonds to carbon if I just put one on each of those carbons. So what happens in an addition reaction is we actually have to make room for those guys that are coming in. So what always happens in this case is our double bond needs to become a single bond to make room for what's coming in. So the good news is you pretty much have the picture right there. We're just going to draw it exactly the way it is and just turn it into a single bond. Now each of those carbons has a spot for those guys that are coming in. And we will put like an A here in my example and an A here. So when you do an addition reaction with an alkene, you basically turn the double bond into a single bond, and one thing comes in and goes to one carbon and one goes to the other carbon, and nothing else changes pretty much. Yeah, so everything else stays the same when we do that. So there's a couple of different types of addition reactions. There's one that is referred to as a symmetrical addition. And a symmetrical addition means that we're going to add the same thing to each carbon, like H2, which is sometimes referred to as a hydrogenation reaction. That means one carbon gets a hydrogen, the other carbon gets a hydrogen. You could add something like Cl2, which is referred to as a halogenation reaction. But basically one gets a chlorine and the other one gets a chlorine. So for example, if we just look at it, something that looks like this, maybe. Why don't we just do this? Let's do this. H2 to it, probably a catalyst and some other things needed. But basically our H2 is we're just going to add a hydrogen to each of the carbons. So although there's a lot of stuff going on in there, there's really only one spot in this picture that changes, and that is where the double bond is located. So that is the only thing that you should really concern yourself with, is that double bond, and you need to make room for what's coming in. So the double bond will become a single bond. Everything else that's on that molecule stays exactly the same. Don't change a thing. That means you pretty much have your picture here that you need right there. You just copy exactly the way it looks. So Could do the H, the C, the CH3, the CH3, the carbon, the bromine, the carbon, the hydrogen. Now my double bond is going to become a single bond, which is the only thing that changes. Going to put a hydrogen, going to do that. I pretty much in 1 second, maybe 5, drew pretty much the picture that I need by copying what was there. So sometimes people overlook the idea that you have pretty much the answer looking at you in your face right there at the beginning. All you have to do is change the double bond to the single bond. No weird stuff happens. This thing doesn't become a ring all of a sudden because it looks more cool or anything like that, you know. It doesn't break apart into 40 different things, you know. It pretty much stays together. The beauty of this is now my carbons have gone from a double bond to a single bond, which means each carbon now can accept the hydrogen that's going to come in. So one hydrogen is going to end up over here, and one hydrogen is going to end up over here. This is a symmetrical addition, which means you can't screw it up. You just need to put a hydrogen on each of those spots because you're adding the same thing. So in this case here, we will put a hydrogen, I'll make it red here, and a hydrogen right there. We go from an alkene to an alkane. Yeah, this is what hydrogenation means. Also what it means when you do something like partially hydrogenate something. Yes, that is making double bonds into single bonds. It also makes it more of a solid in terms of fats, right? That's how you get like margarine, right? From oils and stuff like that. Partially hydrogenated and stuff like that. So this is a hydrogenation reaction. Everything stays the same except double bond becomes a single bond. So why don't you try one here? Why don't you do this? H4. And let's do a little chlorine here in this case. All right, so draw the structure that you should end up with here. Okay, so again, when we look at this, you should know it's an addition reaction, which means you should know, don't make it complicated. What should happen here is just the double bond is your area of focus, and all you have to do is make that double bond into a single bond, and then put one of those things at each of the carbons. So once again, you pretty much could copy exactly what's there, and that's what I'm going to do in this case. I'm going to draw it identical. I'm not going to change anything other than I will draw the hydrogens up, and I'm going to make my double bond into a single bond. And the two hydrogens that I just drew up are those two that were there to start with. The rest of it is exactly the same. At this point, we now have a spot for our 2 chlorines to come in. One's going to go to one carbon, one is going to go to the other carbon. They never go to the same carbon, so they always go to opposite sides of where the double bond was. So here, we'll put them down here with red. Going to put a chlorine and a chlorine. It doesn't matter which one you put on which because it's symmetrical. They're the same elements, so it doesn't matter really which chlorine ends up on which carbon. Any questions on that? Yeah. Say it again. In this case, on the bottom guy there, on the final thing, yeah, there would be no cis or trans in this one because there's no double bond. Yeah, so you wouldn't have to worry about that. And it's back to a single bond, which means, again, it has that free rotation. So you could draw them up, you could draw them down, you could go one up, one down, as long as those. Going to continue on here. So in this case, we talked about symmetrical addition reactions where you just want to remember that essentially you just want to make our double bond into a single bond, and you want to add those things in. We also have addition reactions which are unsymmetrical. And in unsymmetrical addition, we're going to add hydrogen and something else like water, which you could think of as H and OH. We could add something like HCl, HBr. And when we do these additions, it works the same way, except that you do have to think about one thing depending on the situation. So, for example, if we look at this here, and we wanted to add, by the way, water here, which is H2O. Same thing's going to happen. We're going to turn our double bond into a single bond. And once again, everything is going to be exactly the same. And here, the hydrogen in this case is going to be added, and the OH is going to be added. So hydrogen will end up on one, OH will end up on the other. And we will have an OH here and an H, and we go from an alkene in this case to an alcohol. And the functional group of an alcohol is the OH group, is the functional group. And in this case, it really doesn't matter where you put the OH or the H. The other option would have been to put the OH on the left here. And the H on the right. And in this particular case, it does not matter because they're both actually the same alcohol, basically. So if we were to name this alcohol, by the way, we name it just like everything else. So it's got 2 carbons, which is based off of ethane, alcohol, OL at the end. This becomes what is known as, if I spell it right there, ethanol. So that is ethanol. So is this guy, 2 carbons and an OH group. That would be known as ethanol as well, or ethyl alcohol. So they're both actually the same in this case. It doesn't really matter where you put the OH or where you put the H in this particular case. But this is referred to as an unsymmetrical addition because, again, you're adding H and something else to the mix. Now, if we did this with something like HCl, once again, we will turn this into a single bond. So that is the only thing that's going to change. Everything else will remain exactly the same. And now we have room for, again, the hydrogen to end up in one spot and the Cl to end up on the other spot. And in this case, this would be chloroethane, right? And the other one would be chloroethane. There is only one place really for that chlorine to end up. So in this case, it does not matter where you end up with. So if you are going to do this addition to a carbon-carbon double bond where each carbon basically has the same number of hydrogens on it. It doesn't really matter where you put the hydrogen, and it doesn't really matter where you put the chlorine or the OH. You can't mess it up. It'll basically end up on the same one. So if the carbon-carbon double bond's got the same number of hydrogens, you could put those guys coming in either location. It will be okay because you'll pretty much end up with the same structure at the end or same compound at the end. Any questions on that? So very similar to what we talked about before with our symmetrical addition. Unsymmetrical means we get two different things added. This top one is what is sometimes referred to as a hydration reaction. Hydration because you're adding water, and you will always make an alcohol in this case, which will have the OH. Now, it does make a difference when there are different numbers of hydrogen as to where things should end up. So, for example, if we look at something like this and we want to add water to it here. In this case, we're going to take our double bond and make it into a single bond, and we can draw everything exactly the same way. I'm not going to change anything other than double bond into a single bond because frankly, I know I need to make room for what's coming in. Now that I've done that, just like before, I could put a hydrogen here, for example, and I could put an OH here, which gives me my alcohol. Now, the other option would have been if I redraw this thing exactly the way it looks, once again, turning my double bond into a single bond. Oops. And now in this case, I can put my H over here and my OH over here, which comes from my water. So that is your other option. Now, in this particular case, it does make a difference where the hydrogen goes and where the OH grows. These are two different alcohols, and the problem is I got two different products, and I know that because I can name it. So if we were going to name this, how many carbons does this guy have? This guy has 1, 2, 3 carbons. Yeah. And it has an OH group, which tells us it's an alcohol. So that is based off of propane. It becomes what is known as propanol, OL at the end of it, yes. And when we have an alcohol, and especially when we have 3 or more carbons involved, you do have to give the location of where the OH group is located, just like you do with double bonds or triple bonds, which means in this particular case, just like double bonds and triple bonds, we want the OH group to have the smallest number. So in this case, on the top guy here, we would number 1, 2, and 3, which means my OH group is at carbon number 1, which means this is what is known as 1-propanol. That means the OH group is at carbon number 1 in this case. Question on that. So what would this alcohol be called? How many carbons? 3. So still based off of propane. It has an OH group, which means it's an alcohol. So it's going to become propanol. OH group is located at which carbon? Yeah, 1, 2, and 3. This is what is known as 2-propanol. So in this case, our addition reaction here gave us 2 different alcohols. So it does matter where you put the H and the OH, as opposed to what we did here, where it did not matter. You got the same alcohol regardless of where you put that OH. So what is the rule? The rule is what's referred to as Markovnikov's rule, which says that when you're adding hydrogen and something else like OH from water, our Cl or Br. The hydrogen will end up at the carbon that had the most hydrogens to begin with. So the hydrogen goes to the carbon that had the most hydrogens to start with. Which, by the way, is in the double bond. So this carbon over here has how many hydrogens directly attached to it? 2. This carbon has how many hydrogens directly attached to it? Only 1, this guy. So the real product that we should draw is actually the one where the hydrogen ended up over here on that carbon, as it had more hydrogens to start with. And that would give us what is referred to as the major product, which is usually what you want to draw. This is what is sometimes referred to as the minor product, which you usually don't want to draw too much. So this will give us the major product. So when you're adding this unsymmetrical addition and there's a difference in the number of hydrogens in that double bonded carbon, the hydrogen coming in should always end up at the carbon that started with the most hydrogens. Question on that thing. Okay, so let's take a look. So once again, we just want to focus in here on our double bond. We got an addition reaction happening. So we should know that we're just going to turn our double bond into a single bond to make room. And once again, you pretty much have 99% of the picture done for you over here. So just copy exactly what it looks like. So we're going to do our CH3, our carbon, our CH3. Once again, we're going to turn this into a single bond. And everything else is, again, exactly the same in this case. We're going to add H and OH in this case, in this hydration reaction. This case, the hydrogen doesn't matter where it goes. It does matter where it goes because this carbon has no hydrogens, right? This one has 1. Now that I got rid of the other one. And that means that the hydrogen here should actually end up on the carbon on the right-hand side. So we should put the hydrogen here, and that means that the OH should end up over here at this guy right there. Question on that. And again, we made an alcohol here through this hydration reaction. The name of this alcohol would be, that is 4 carbons, which is based off of butane. It is an alcohol because it has an OH, which means it's going to be butanol. We do need to give the location of that OH group, which means it should be at carbon number 2 in this case, which gives it the smallest number. That is 2-butanol because the OH group is at carbon number 2. There is actually one more thing there, right? And that is a methyl group, which is also at carbon number 2. So this would be 2-methyl 2-butanol. Yeah. Any question on that name there? So in this case, we would want to put the hydrogen on the right there, as it does make a difference here. How about in this situation here? We're going to turn our double bond into a single bond. Doesn't make a difference where I put the hydrogen on this one. It does, because this carbon is starting with how many hydrogens attached? 2. And this carbon is 1. So here the hydrogen should end up on the carbon on the left or right? The right-hand side. That's going to be our hydrogen. That's going to be our Br in this case. Any question on those addition reactions? So symmetrical addition, basically remove the double bond. Doesn't matter where you put it because you're adding 2 of the same. So just put 1 on each carbon. Unsymmetrical, same thing happens. It just means you're adding hydrogen and something else. But again, you take the double bond to a single bond, and 1 goes to one carbon, 1 goes to the other. The only additional thing here is if there happens to be differences in the number of hydrogens to start with, then the hydrogen should always end up at the carbon that had the most hydrogen to begin with. That's known as Markovnikov's rule there. Any questions on that there? All right. So since we sort of jumped a little bit into alcohols here, and it is the lab this week, we're going to kind of go into a little bit of the next chapter, which is about alcohols, and then we'll come back and finish the rest of the slides here next time, I think, on this chapter. So I think what I'm going to do is just use a bunch of these things right here. I like it. All right. So since we started talking about alcohols and it is the lab of the week, I think this will kind of follow the next handout, but I'm just going to kind of go from the top of my head since we just have a few minutes here, or 15 minutes to go, and then we'll go over the handout officially as we go through it next time as well. But alcohols have a functional group of the OH group, and that OH group is a polar group. If you remember from bonding, difference in electronegativity, oxygen is more negative, hydrogen is more positive. That makes alcohols soluble in water. Very low carbon number alcohols are soluble in water, because if you have something like methanol, it is able to hydrogen bond with something like water. Again, this being more positive, this being more negative, negative and positive here. So that is going to be able to make a hydrogen bond, which will allow something like methanol to be soluble in water. Something like ethanol will also be soluble in water. But the solubility of alcohols starts to drop right around 5 or so carbons. And that's because as you build out a ton of carbons in an alcohol, and you just got this one little OH group at the end, solubility decreases to kind of nothing at that point. And it is because your alcohol is frankly too big. And the alcohol basically has two parts. It has this part, which is nonpolar, and it has this little part in this case that is polar. So in the case of methanol, methanol is a relatively small molecule overall, which means it will not have trouble interacting with water. But as you build out that nonpolar size with all those carbons and hydrogens, it gets in the way of water being able to get to that OH group. Creates what's sometimes referred to as steric hindrance. It's kind of like too big and moving around. Plus, in order for something to be soluble in water, it needs to be able to replace water and water interactions with similar type interactions. So water is a relatively small molecule. You try to put that guy in the mix, it's not going to mix really well. So it's kind of like, you know, you could put a car in a garage, but you try to put a semi truck in the garage. Doesn't really fit so right? It could get some of it in there, but it's not going to work so well. So what happens is as you increase the nonpolar part of alcohols, it gets too big to interact well with water, and solubility pretty much drops to nothing. Usually around up to like 4 or 5 carbons, you're still okay in terms of solubility, and then you start to see a pretty big decrease in the solubility as well. Alcohols, in addition, have usually really high boiling points. And alcohols will typically have high boiling points because they can actually hydrogen bond with themselves. And hydrogen bonding, if you remember, is a pretty strong intermolecular force. So again, the negative, positive, positive, negative. And again, it can hydrogen bond with itself. So it usually has very high boiling points. And that is because the hydrogen bond is really strong, so it takes a lot of energy to break it apart. The result of that is a much higher boiling point than anything. It is almost a champion of organic compounds, except there's only one that could beat it or so. But everybody else pretty much will have a much lower boiling point because they don't have the ability to hydrogen bond. There is a couple of things that could one or two things that could get a higher boiling point, but it's usually pretty much up there towards the top in terms of organic compounds. If you're comparing it, for example, to an alkane or an alkene or an alkyne, they cannot hydrogen bond. So they have very low boiling points. In order to hydrogen bond, you need a bond between hydrogen and nitrogen, oxygen, or fluorine. So just because something has hydrogens, they cannot hydrogen bond. So something like methane here, even though it is loaded with hydrogens, it cannot hydrogen bond because it is not bound directly to a nitrogen, oxygen, or fluorine. It's actually a nonpolar molecule, which means it's not going to hydrogen bond at all. It's actually going to use dispersion forces, which is really weak intermolecular forces, and will have a very low boiling point because of that. So alcohols are kind of the champ there in terms of boiling points because of its ability to hydrogen bond. Also, low carbon alcohols are good in terms of being able to be soluble in water. Any questions on that there? Alcohols, just like carbons, can be classified as primary, secondary, or tertiary alcohols. And it is kind of the same idea. In this case, what you're looking at is the carbon that has the OH group attached. How many carbons are directly attached to it? And in this case, there's one. So this is what's referred to as a primary alcohol. If you have an alcohol like this carbon, which has the OH group directly attached to it, is attached directly to 1 and 2 carbons, which makes it a secondary alcohol. And lastly, if you had an alcohol such as this, this is the carbon that has the OH group. It is attached to 1, 2, and 3 carbons. This is a tertiary alcohol. So you kind of count alcohols, primary, secondary, and tertiary, like we do carbons. The key here is you're looking for the carbon that has directly attached to it the OH group, and then how many carbons are directly attached to that carbon. So again, 1 carbon would be a primary alcohol, 2 carbons directly attached to a carbon that has the OH group is a secondary alcohol, and 3 carbons attached to the one that has the OH group would be a tertiary alcohol. Question on that there. So if I had this guy here, this would be a primary, secondary, tertiary alcohol. It is a secondary. This is the carbon that has the OH group attached to it. It has 1 and 2 carbons directly attached to it. It would be a secondary alcohol in this case, yeah. Question on that there. So again, you're not looking at the OH group as to how many carbons are attached to the OH group, but you're actually looking at the carbon that has the OH group attached, how many are attached to that carbon. Any questions on identifying those? All right, so we did talk about sort of naming here. So we do obviously end with OL. We do give the priority to the OH group in terms of numbering. So if we had something like this, this would be called what here? Longest carbon chain is how many? Longest carbon chain is 1, 2, 3, and 4, maybe. Yes. You get 4 a number of different ways, but 4 looks like a winner no matter which way you go. You could go straight and then down will give you 4. You could go that way and down will give you 4. You could even go just like that in the middle, and that will give you 4 as well. but it does look like 4 is a winning number here. So once again, 4 carbons is based off of butane. So it's going to be now butanol. We have an OH group, and we got a bunch of other guys hanging out there. Yeah. So we want to number this. Should I go left to right or right to left here? Left to right will give the priority to the OH group, a smaller number, and that would be 2 butanol for the location of where that's at. That means I do have 2 methyl groups, right? So that's going to be a dimethyl. And those methyl groups are at carbons number 2 and 3 in this case, right? Over here, I have a bromol group at carbon number 3. That's pretty much all I need to name this guy. Which one should go first? Alphabetically, which group? The B before the M, right? So we don't look at the prefix. So this is going to be 3-bromol, 2,3-dimethyl, 2, I'm running out of page here, butanol. What happens when you just make up something and go after it? I don't know. So we got 3-bromol, 2,3-dimethyl, 2-butanol. Any questions on that name? By the way, primary, secondary, tertiary alcohol here. I think I heard tertiary, and I would agree with you. That is the carbon, right, that we're looking at. It is attached to 1 carbon, 2 carbons, and 3 carbons. This would be a tertiary alcohol. Any questions on that? Yeah. No, we won't come across anything like that. So it would be 1 functional group at a time. The only one that you might come across that has some double bonds in it is a special alcohol, which is this is really the benzene ring. Looks like this. Or sometimes they will draw it with just a circle in the middle. And if you have this guy with an OH, that's what's known as phenol. And that is an alcohol, and it has a special name. So that'll probably be the only one that would have it. You could also have a ring type structure, for example, that would be called cyclohexanol. Yeah, so this would be cyclohexane basically, because it has an alcohol group that would then become cyclohexanol in that case. That is not phenol because there is no double bonds in the middle or circle. So don't get those two confused, which is very commonly confused. By the way, if I had another group attached there, when you just keep adding to this guy, what would that then be called? The OH group should take the priority, which means this should be carbon number 1, and that chlorine should then be at carbon number 2. So this would then become 2-chloral cyclohexanol. Yeah. So the OH group you don't need to number in a ring structure, but it is carbon number 1 for sort of assigning everybody else. In this case, because there's no double bond, you could go either way, clockwise or counterclockwise, to give it the smallest number. So you don't have to worry about going through any type of double bond in that case. Question on that, or naming of these guys. All right, to finish up, let's talk about 3 common reactions that these guys undergo. We also saw earlier here how we make an alcohol. An alcohol is made by adding water to an alkene, right? So that's the addition reaction. So that is how we make an alcohol, is to basically hydrate a double bond, and you get that OH like we were doing previous to this. A primary alcohol will be oxidized. And when we talk about oxidize, we talked about some of the definitions earlier on in the semester. But in this case, what we are talking about is the loss of hydrogen, is basically the oxidation reaction. So if we take a primary alcohol like this guy here, I'm going to draw the hydrogens out here like so. Actually, I'm going to draw it the other way so it'll be easier to see. I'll put my OH group up on top. You don't have to, but I might make it easier to see this here. We'll do that. So if we go through an oxidation, which is sometimes referred to as this little O in a box, we're going to lose hydrogen. And we're going to lose H2 in this case. And where the hydrogen is lost from is, it is always lost from the hydrogen on the OH group and a hydrogen on the carbon that is attached to the OH group. So I'm going to take off those two, and that's going to give me my H2. By the way, nothing else changes on that molecule I just did there. Everything will be exactly the same, which means I'm going to copy what's there on the left, except for the hydrogens. So I should have a CH3, I should have a C, I should have an O, and I should have an H. So I got rid of my two H's, one from the OH, one from the carbon that's attached to the OH. I drew everything exactly the same, except I have a little problem here. The carbon there only has 3 bonds. When we make a double bond, right? We take away 2 hydrogens, right? To make that double bond. So when we remove 2 hydrogens, we need to kind of put the double bond back on. So what's going to happen is we're going to make a double bond. I'll make it in this color here, right there. That's going to be a double bond that's going to happen. So in a oxidation of a primary alcohol, you take 2 hydrogens off, one from the OH group, one from the carbon that's attached to the OH group, and you always put the double bond between the carbon and the oxygen. So then you lay up a double bond between the carbon and the oxygen. This makes a type of compound which is known as an aldehyde. An aldehyde has the functional group of the carbon-oxygen double bond, and the hydrogen is the functional group of an aldehyde. So if I take a secondary alcohol, like this guy, and I put it through an oxidation reaction, the exact same thing is going to happen. I should take a hydrogen off of which file? Hydrogen off of the OH, right? The other hydrogen should come off of the carbon that's attached. So those two are coming off. Always happens that way. I am left with the exact same structure I have there, except take off the hydrogen. So I'm going to draw it as exactly the way it looks. I'll leave it like that. And now what should I do between the carbon and oxygen? I should make it a double bond. Yes. Trust me when I tell you, don't overcomplicate the drawing of these things. Keep it very simple. Yes. So make a double bond right about there. That, by the way, is what is known as a ketone. The functional group of a ketone is 3 carbons in a row with a carbon-oxygen double bond happening. And in case you can't see it, that is 1, 2, 3 carbons in a row with the carbon-oxygen double bond happening. So you make a ketone. So if you oxidize a primary alcohol, you get an aldehyde. And if you oxidize a secondary alcohol, you get a ketone. Both reactions are exactly the same. Remove those 2 hydrogens and put the double bond between the carbon and the oxygen, and you will have the right product drawn. And it should look exactly the same. You could straighten it out if you wanted to. You could draw this guy just like this, and you could see probably the ketone a little bit better. But again, there's our 1, 2, 3 carbons in a row with our carbon-oxygen double bond gives us a ketone. By the way, just in case you want to name this, this is how many carbons? 2. And 2 carbons is based off of ethane. This is what is known as ethanol, AL. That's how you name aldehydes. You do Al, not Ol, which are alcohols. By the way, this guy right here has how many carbons? 3, which is based off of butane. This is what is known as butanone, O-N-E. It's how you name ketones. Ketones and then O-N-E, that is how you name them. You put O-N-E at the end of it. So that is butanone as well. You do have to give the location of the carbon-oxygen double bond starting at like 4 carbons, but other than that, it's the same thing. That leaves us our tertiary alcohol. And if we had a tertiary alcohol like this guy right about here, and we go to oxidize this being our tertiary alcohol, remember that when it goes through an oxidation, we need to remove 2 hydrogens, 1 hydrogen from the OH, right? The other hydrogen from the carbon. Is there a hydrogen? No hydrogen. No hydrogen there. No reaction there. Yes, you need both of those hydrogens in each of those locations, 1 in each location. So a tertiary alcohol will actually not go through an oxidation reaction.